So let's do some definitions first. A walk is going to be a sequence of vertices with the property that each vertex is adjacent to the next vertex. So in particular, it's okay for pairs of vertices to repeat in a walk. We're going to call the walk closed if it starts and ends at the same vertex. A trail is going to be a walk with no repeating edges, whereas a path is going to be a trail that has no repeating vertices. And a circuit is going to be a closed trail, so it's a trail that starts and ends at the same vertex, whereas a cycle is going to be a closed path, a path that starts and ends at the same vertex. And in all cases, we're going to refer to the lengths of these types of mathematical objects to be the number of edges. So here is a graph. I'm going to claim that this sequence here is a walk. So I'm starting at A, I go over to C, down to D, down to B, down to A, back down to B, and then over to E. So it's a walk from A to E. I notice that I repeat some vertices and I traverse the same edge twice. Now an example of a closed walk would be starting here at E, I go up to D, then to H, then to B, then down to E, then the D to B, back to E. So I go along this four cycle, or this quadrilateral, and then along this triangle. So I start and end at E. On the other hand, an example of a trail would be E goes to D, goes to B, goes to A, goes to C, goes to D. In that walk, I never repeated an edge, so it is a trail. On the other hand, I did repeat a vertex at least twice. So a path would be like going from B to A to C to D. In this case, I never go through the same vertex twice. Meanwhile, that's not, in order to make that path into a cycle, I just need to add the step from D to B. So B, A, C, D, B. So we say that a graph is connected if for any two vertices in your graph, there exists a path from U to V in the graph. I'm going to say two vertices are related if there's a path between them. And you can prove that this relation is an equivalence relation. And we usually refer to those equivalence classes as components of the graph. So in other words, given a vertex, its component consists of all other vertices you can reach from that vertex. So for example, consider the graph we've been working with. If I take the vertices A and C, I can create a path between them. And in fact, you can see with any two vertices on this graph, it's possible to connect them by a path. On the other hand, if I were to remove the vertex E and pretend it no longer exists, then I see that there's no longer a way to get from A to C, because every path from A to C has to go through the vertex E. So that would be an example of a disconnected graph with two components. So now we arrive at a theorem for this video. We're going to show that every xy walk, so a walk from x to y, must contain an xy path. The advantage of this theorem is that in some instances it turns out proving that a walk exists is going to be easier than showing that a path exists. So knowing that a walk contains a path allows you to get to the path conclusion you want. So we're going to prove this result by induction on the number of edges or steps in the walk W. So in the base case, there are no steps in the walk. Then that means the walk must be starting and ending at the same vertex, because that's the only vertex on the walk. And so then that trivially is an xy path. So for the inductive step, I should write down what our inductive hypothesis is. For some positive integer k, we're assuming every xy walk of length less than k contains an xy path. So now what are we going to do? We're going to take a walk of length k and show that it also contains a path. So let's take our walk. We'll call the vertices v0 through vk. And of course, if it's an xy walk, v0 must be x, and vk must be y. We, of course, first note that if the vertices on this walk are distinct, so vi is not equal to vj, whenever I is not equal to j, then the walk is a path and we have nothing left to show. So then the only remaining case is that we have vertices repeating on the walk. Or in other words, there exists an I less than j where vi is equal to vj. So in other words, we have something like this. You start at v0, you go up to vi. Who knows if some crazy stuff is going on before vi. Then once you go past vi, we go along this little trail, and then we come back to vi again at vj, and then we keep going. So the point is that if we skip this little segment here, we're going to get a shorter walk. So we go from v0 to vi, and then since we see that vi is adjacent to vj plus 1, we can go to vj plus 1 and then continue on the walk up to vk. And so since we've removed at least one vertex, w prime has shorter length. So by the induction hypothesis, we see that there must be a path in w prime, and thus a path in w. So w prime does contain an xy path, and thus so does w. And now I have to introduce a concept that right now seems a little mysterious, but we're going to use it in the next proof. In graph theory, there's a difference between using the word maximal and the word maximum. So suppose you have some property P, like being connected or being a path, then a subgraph in G is called maximal for that property if that subgraph satisfies the property, and yet all larger subgraphs containing the subgraph you started with fail that property. So in other words, you have a subgraph that satisfies the property, and there's no way to add vertices to the graph to get a larger one that does. On the other hand, when we say something is maximum, that means that not only does that subgraph satisfy the property, but any larger subgraph fails that property. So example, let's look at this graph here and look at the path in red. I claim it's a maximal induced path because if I add any other vertex to the red graph, what I will end up getting is the new induced subgraph will no longer be a path. So if I add this vertex, it's no longer a path because there's a vertex of degree 3. If I add this vertex, I end up with a cycle. However, that is not the maximum length path because it's clear that you could create one that's longer. All right, so here's our proposition. Suppose that every vertex in your graph has degree at least 2, then we claim that the graph must contain a cycle. We will use this result in the next chapter. So the proof is to consider a maximal path. So that means that we've got a sequence of vertices that forms a path on our graph, and that we can't make that path any longer, which means if we take any vertex that is adjacent to either the start vertex or the ending vertex of the path, then that vertex has to appear on the path. The reason why that is because if you had a vertex that was adjacent to v0 that's not on the path, then you see that you could make your path bigger. So your path wouldn't be maximal. So this means that all the neighbors of v0 have to appear somewhere in the path. All the neighbors of vn also have to appear somewhere in the path. Since the degree of v0 is at least 2, because of our assumption, we know that v0 has a neighbor on the path that isn't v1. So that means that we must actually have this blue edge for some vi. And then the rest of the proof is to just go ahead and start at v0, follow the path till you reach vi, and then go back to v0, and congratulations, you have a cycle. To be fully correct, you see that you have a closed walk, but you can guarantee there's no repeating vertices because if a vertex repeated somewhere in here, then that vertex was already repeating in your original path, contradicting the fact that we picked a path and not a walk.